All right, Calc BC. Welcome to lesson 3.7, the area between curves. All right, so we know very well at this point how integrals can help us find the area under a curve. What if we have two curves and we want to find the area between them? Well, it's a pretty simple concept, but this specific skill comes from Unit 8, Applications of Integration from College Board's version of our units. And we're going to be looking at three different kind of topics all in one: finding the area between curves expressed as a function of x, expressed as a function of y, and curves that intersect at more than 2 points. And just for example, here's one of the topics from College Board, and you can see here the essential knowledge is areas of regions in the plane can be calculated with definite integrals, and that's what we're going to be doing today. So I'll pause this and pull out the notes. All right, so here are our notes for 3.7, the area of a region between two curves. And let's take a look right at the top. So I already drew two curves on here, and what we're going to be trying to figure out in this lesson is how do we calculate the area between these two curves. So right now, all we really know is how to find the area between a curve and the x-axis. But what if we have more than one curve or more than one line, and we're trying to find the area between them? So to find the area bounded by two functions, f of x and g of x, we are going to use an integral. But I want to start just by kind of explaining what we're looking at here. So let's say that this intersection point over here has an x value that we're calling a, and that this intersection point over here has an x value that we're calling b. Right now, we know if we just wanted to find the area under the blue curve, right, the top one, we would use an integral from a to b of f of x dx. And what that's doing is it's slicing this area into incredibly small sections, like a Riemann sum with infinitely tiny bars, and it's adding all of them together, right? So we found that whole area. If we wanted to find the area of the orange curve, the lower curve, between that curve and the x-axis, we would do the same thing, right? We would go from a to b, integral of g of x dx. And what that would do is give us all of the slices under the orange curve. Okay? And hopefully it makes sense then that to find the area of just the part that's shaded blue, what we're going to do is subtract the two regions. So you can write it like this. We can have the integral from a to b of f of x dx minus the integral from a to b of g of x dx. But normally, this is written as just one combined integral, right? Because we know that if we're subtracting two integrals with the same bounds, we can combine. So we're going to rewrite this as from a to b f of x minus g of x dx. Okay? The most important thing, though, is that the first function that you put in here is always the upper. The second function that you put in here is always the lower. So that's what we're looking at here. This next part is when we had a region that is bounded by two functions, and we're going to go in the y direction. We're going to come back to that and just apply that first section first. So let's try this first example down here using this formula. So we've got the directions here. Find the area bounded by the following graphs. Draw a figure and shade the bounded region. So first up, we have y equals 3 minus x squared. So I will do that in orange. First, I'm going to make a rough coordinate plane here. So we got 3 minus x squared. That's going to be a parabola opening down. That's moved up 3 units. Okay, and you can just plug in some x values if you want. So if we plug in 0, we get 3 minus 0 is 3. We plug in 1, we get 2. We plug in 2, we get -1. And that should be good enough. So I'm going to just kind of finish sketching there. And then our other curve is actually a line. Y equals -x plus 1. So for this one, it has a slope of -1 and a y-intercept of 1. Okay, so you can see when I connect the dots, we've got a straight line here. And there we go. And we're going to shade the bounded region. So you can clearly see right here is our bounded region. I'm shading it vertically because that's the style of slices that we're going to be making here. And for this type of question, the intersection points are extremely important. And you can see right here, we have an intersection point of 2, -1. And right up here, we have an intersection point of -1, 2. And the reason that's important is because that gives us the left and the right bound for our integral, right? The x values will tell us when to start and when to stop. So we're going to go from -1 to 2. And so let's check that out. So we're going to have the area equals the integral from -1 to 2. And again, that's because the x values are what matter here. We're going to go from an x value of -1 to an x value of 2. It doesn't matter that these ordered pairs have any given y value. We don't really care about that when we're setting up the integral, only the x values. And so we're going to, inside of here, put the upper minus the lower. So in this scenario, the upper part of the curve is 3 minus x squared. The lower part is -x plus 1. The parentheses are very important because that will make sure that this negative gets distributed, so we just subtract the whole line. Now, something that I think of when I see this question is that we have part of our area that's below the x-axis. So the way that we originally sketched this, everything was above. It doesn't really matter if anything's above or anything's below the x-axis, as long as the orange curve is always above the blue line, because that's how we set up the integral, then this is going to work. So anything that's a negative area is going to automatically kind of cancel out and give us just the positive area between these curves. Okay, the integral is going to take care of that for us. So let's see what happens. So I'm going to distribute the negative and combine like terms here. We end up with -x squared plus x, 3 minus 1 plus 2. And then I'm going to integrate. So I'm going to get -x cubed over 3 plus x squared over 2 plus 2x from -1 to 2. And when I plug these numbers in, if I plug in 2, I'm going to end up with 10/3. If I plug in -1 for all of the x's, I'm going to end up with -7/6. And so I can do 10/3 minus -7/6, and I get 9/2. So that's officially the area between these two curves. And that's how we do it, okay? So what the math really did was take the area under the orange curve and subtract the area under the blue line to give us the area between the curve and the line. All right, so that's how we do that. However, it's not always that simple, right? Things are going to get more difficult. So in the next question, it's not really going to make much sense to integrate this in the x direction. So let me show you what I mean by this example up here. I sketched two different, well, a curve and a line here. And this is just a rough sketch, right? I don't even have equations for any of these. But think about how we would integrate this if we thought about it being between two curves with an upper and a lower. So if I'm looking at this coordinate plane here, remember we care about the x values only. So from right about here to right about here, you can see that the blue is above the orange. So we would do blue minus orange and we'd be fine. We'd be getting the area in here. But then from here to all the way over here, we have a different issue. The upper curve would be the blue curve and the lower curve would also be the blue curve, right? We've got an issue. And we're gonna learn in a couple minutes or potentially tomorrow, depending on how this video gets split up, that sometimes you do need to have more than one segment of your area if the upper and the lower switch or change. And in order to do that, we just add more than one integral together, separating at all the intersection points like this would be. But this isn't really ideal. We don't want to have a blue curve over the blue curve. So sometimes it's just much easier to think of it as functions of y instead of functions of x, and to think of your whole graph sideways. So if we just shift this so that now our x-axis is going up and going down like the y-axis normally does, take a look. And if I kind of shade in my slices here, we have the endpoints, and now we have one upper curve and one lower curve, and we don't have to worry about doing more than one or anything crazy. I'm going to do some brief slices this direction. And orange slices this direction. I could go for some orange slices right now. Okay, and then I shift back so my page is the right orientation. What you'll see is that if we take that blue area and we subtract the orange area, you'll get just this blue only chunk, which is what we originally wanted. So I'm going to write this out the same way that we did before. We now have an a and a b that are y values instead of x values. So we've got the integral from a to b of f of y dy minus the integral from a to b of g of y dy. And once again, we are going to write that so that it's just one integral, so we're going to combine it. And it's very important this time that the first function is always the one that's to the right. The second function is always the one that's to the left. So to the right and to the left. And that's going to make sure, because to the right is bigger x value. So that's going to be kind of serving as our upper function in this case when we kind of shift it sideways like this, right? Okay, so that is how we're going to approach letter B. Let's take a look at letter B. So letter B says that x equals 5 minus y squared and x equals y minus 1. That's our two functions. Well, that's our two equations. A function would imply that it passes the vertical line test, which one of these doesn't, which we'll see. But anyway, we're going to find the area bounded by the graphs, draw a figure, and shade the bounded region. So let's try that for this one. So in this question, first of all, we need to figure out how to graph these. So something that we could do if we wanted is to solve them for y equals, so that we know how to graph them normally. I'm going to sketch my tick marks to start. And I'm going to make this first one orange. So we've got x equals 5 minus y squared. If I wanted to solve that for y, what am I doing here? So I subtracted 5. I'm going to make it negative, so it'll be negative x plus 5 equals y squared. So y equals plus or minus the square root of negative x plus 5. Okay, so you could try to graph that on your graphing calculator if you wanted to see where it is. But I'm going to think about it just in this context, and I'm going to think this is kind of like a sideways parabola, and it's going to be opening down, which is like this direction, and it's shifted up 5. So it's really going to be 1, 2, 3, 4, 5 like this. It's going to be going left 1 there, and then it'll go to 1 comma 2 and 1 comma negative 2. And if you're not quite sure about that, remember, you can always just plug in values and see what you get. So if I plug in this case, it's going to be easier if I plug in y values. So if I plug in 0, I get 5 for x. If I plug in 1 for y, I get 4 for x. So it gives a point at 4 comma 1. And we can keep going like that. We are going to need one further point. So if I plug in 1, 2, 3 for y, I get 5 minus 9, so negative 4 for x. So it's going to be all the way over here. Okay, so I'm going to connect that curve. So it looks like that. And then let's try this one. So we have x equals y minus 1. I add 1 to the other side, and I get x plus 1 equals y. So that's a pretty simple line. It has a y-intercept of 1 and a slope of 1. So we can go like this. And connect the dots. And you can see that this question is one of the kind where it's much easier to think of the shaded region as the upper being to the right and the lower being to the left than it is to think of like a standard upper and a lower function, because it doesn't stay the same. Like this has an upper and a lower that are unique over here, and then over here the upper and the lower are both orange. It's just going to be easier to do it in the y direction. So we need to know our endpoints. This one is 1 comma 2. And over here we have 1, 2, 3, negative 4, negative 3. And let's see, we're going to be slicing in the horizontal direction this time. So I'm going to shade with horizontal slices. And then it is time to set up our integral. So our area. This time, we're going to use the equations that are solved for x so that we have the variable y in it. And when we do the bounds, just like we put up here, we're going to go from a to b. The y values, so it's going to be from negative 3 to 2. And inside we put the function to the right, which was 5 minus y squared, minus the function to the left, which was the y minus 1. And I'm going to then solve this integral. So I'm going to combine like terms. And integrate. And then we'll plug in the 2 and plug in the negative 3. So once you do that, when I plug in 2, I'm going to get 22 thirds. When I plug in negative 3, I'm going to get negative 27 halves. So you combine those fractions, and we're going to end up with 125 over 6. So that's the area of that purple region. Okay, so the next question that we're going to do is to show how we can use a calculator to get some of this. But before we do that, I wanted to show you that let's say that on the graph we couldn't tell what these intersection points were. Maybe we didn't graph very neatly, or maybe it's just not easy to tell what the intersection points are. Another way to figure out the intersection points is to set the functions equal to each other and then solve. So in a question like letter A, we'd be solving for the x's. So it'd be like 3 minus x squared equals negative x plus 1. And when we solve that, what would happen? Let's move it to the right. So we have x squared minus x, subtract 3, so we get minus 2. And we get 0 equals x minus 2, x plus 1. So x equals 2 and x equals negative 1. That tells us that the two x values where we have intersection points are negative 1 and 2, which is how we could get the bounds here. We could do the same thing in letter B if it's in the y direction. We set the two equations equal to each other. Solve for y. And we get y plus 3, y minus 2. So we get y equals 2 and y equals negative 3. And you can see, once again, that's our two bounds. That's the two y values where we had intersection points. Okay, so that's another way to find the bounds of your integral. And that is going to help us with the next question. So if we flip on over to letter C, we have f of x equals x to the 6th and g of x equals x plus 2. Use your calculator. So let's do that. So I am going to first graph these on my graphing calculator. So I'm going to have x to the 6th. Oops, let me make that y1. And x plus 2. So I'm going to graph those and see what happens. Okay, x to the 6th looks like similar to a parabola. And then we have a line. Okay, that was to be expected. I'm going to zoom in a little bit. Hopefully I didn't chop off any of our overlapping region. I did. Oh no. Okay. Just going to go back to this thing. We'll just have to deal with it. Okay. So the first thing I'm going to do is just do a rough sketch of this. I'm not going to make it super specific this time. I'm just going to do a rough sketch. And we have our x to the 6th, which kind of goes like this. And then we have our x plus 2, which looks like this. So this was f of x, this was g of x. The reason I'm not really worrying too much about this is because we are going to find the ordered pairs of the intersection points using the calculator, not based off of our graph this time. So on the calculator, I'm going to go to second trace, number 5, intersect, and I'm going to find the intersection of both points, of both curves. So the first one is at negative 1, comma 1. And the second one, if I go back to second trace, number 5, move my cursor so that it's close to the second intersection point, enter, enter, enter. We have, I'm going to round to 3 decimal places. So we have 1.215, comma 3.215. Okay, so let's use those to find this area in here. So we're going to use the integral from x values of negative 1 to 1.215. And we're using x values because you can see in the x direction, or when we have vertical slices, we clearly have an upper and a lower part of our curve that we'll be able to use equations for. So let's plug that in. So we have the upper is the x plus 2 this time. You can see that's the line, minus the lower, which is the x to the 6th, dx. So I'm going to just, without even doing anything else, I'm just going to plug that into my calculator, see what I get. So I'm going to go to math 9, negative 1 to 1.215, and just plug this in. So we have x plus 2 minus x to the 6th dx. And that should be good. Yep, I got 3.967, and that's what we want. Okay, so that's how you can do this using a calculator for some of the more complicated questions. Last example. Set up the integrals needed to find the area of the shaded region. All right, so let's say that we had an x-axis down here that isn't showing up. Here's our x-axis. And what we're interested in here is all of the intersection points, right? We've got a point here, we've got a point here, and we've got a point here. So there's actually two segments of the shaded region in this question. And we're not going to be able to do one integral with an upper and a lower curve in the x direction or the y direction. So in a question like this, we're actually going to have to make two different integrals. So I'm going to label these x values as a, b, and c. And so our area is going to be the integral from a to b. And from a to b, the upper curve is the g of x. And the lower curve is the f of x. And we're going to add the integral from b to c. And this time, the upper curve is the f of x. And the lower curve is the g of x. So if there's more than one chunk to your area, or the upper and the lower switch, you're going to have to switch it up just like that. Okay, so hopefully that makes sense. That, once you calculate, would give you the area of the purple shaded region. And that's it. That's all of the notes for this lesson. So if we think about the worksheet, most of the worksheet is going to be pretty good for you. When you get to some of the later questions, sometimes there are more than two curves listed or more than two equations. And if that's the case, take a look at the graph, because there's still always only one upper and one lower part of the region at a time, right? There's an upper and a lower, or maybe it's to the right and to the left. But even so, you should be able to figure it out without any other formulas. So if there's three different equations, just look at the region, figure out what the left and the right bound are, and the upper and the lower functions, and you should be good to go. Okay, so let me know if you have any questions. Good luck. As always, the answers are on Schoology, and hope you have a great day.